3.2 maximum and minimum on an interval, okay, also known as extreme values. One of the purposes of finding the derivative of a function is to solve for a maximum, or like the largest value, or the minimum or smallest value. Okay, absolute extreme. When we talk about an absolute extreme, that's the maximum or minimum value on an interval. Oh, sorry, absolute extreme. Okay, so let's do a little bit of an investigation. For the following function, determine the max and min by completing the square. Okay, so completing the square is definitely a grade 10 and grade 11 approach to finding the max or min of a quadratic, which is the vertex, right? So what we're going to do is we're going to convert this parabola into vertex form. So f at x equals negative x squared plus 6x minus 3 on the domain 0 to 5. So f at x equals, in completing the square, we group the first two terms, we divide by -1, so negative x squared minus 6x. Okay, don't pull out the x, and then minus 3. Now what we do is we take this x value, we take it to the side of our paper, and we divide it by 2 and then square it. This is how we actually complete the square. So we get 3 squared, which is 9. So what we do back into the equation is we add 9 and then subtract 9 inside of the bracket. What this is doing is it's adding 0. So our equation doesn't actually change. It's just changing the way the equation looks. Okay, you can add 0 to any equation. Now, this -9, we're going to pull it outside of the bracket, but because it's inside the bracket and there's a negative sign attached to the bracket, we multiply by -1. Okay, so we are left with negative, this trinomial here, x squared minus 6x plus 9, then on the outside of the bracket, minus 3 plus 9. Okay. Now, let's go ahead and factor inside of the bracket. We're going to get x minus 3 squared, and minus 3 plus 9 is going to be positive 6. Our vertex here is 3, 6. Okay, so what that means is that we have a maximum value of 6, which occurs at 3. So max value of 6. One more step that we have to take when we're actually solving for the max or min values is we have to go ahead and sub in the endpoints. So let's sub in f at 0, which is going to be our starting value. Okay, and we get, so 0, 0, -3. Right, that's going to be the y-intercept. And let's sub in our end value. Okay, which is going to be f at 5 equals 2. Okay, so this is a whole picture of what is going on here. So from 0 to 5, let's put this over here. Okay, so from 0 to 5, we have the parabola where 0 is -3, 5 is 2, and the vertex is 3, 6. Okay, so this is our parabola. Do you notice that this is not centered? Okay, so we can't always tell if, for example, if the vertex is in the domain, okay, because it's not centered. So that is the grade 9, grade 10 way of doing this. Now, why don't we find the derivative of a and let the derivative set it equal to 0. Okay, so let's rewrite the original so that we can scroll down. F at x equals -x squared plus 6x minus 3. So if we were to take the derivative, We bring this 2 down, we get negative 2x. Derivative of 6x is just 6, negative 3 goes away. Okay, so our derivative, or our velocity function, f prime at x, is negative 2x plus 6. If we were to take this derivative function, aka the velocity, and set it equal to 0, what we're going to get is, after rearranging, x equals 3. Okay, so what do you notice? X equals 3, x equals 3. So the velocity at time t equals 0, or in this case, f prime at 0, f prime at x equals 0. Okay, when we set it equal to 0, we get the x value at which the function, we can say like turns around. For this specific function, because it is a quadratic, we can say vertex. And we get that this is, like for this function, x equals 3. So the maximum value of a function that has a derivative at all points in an interval occurs at a peak. So what this peak is called is a maximum or a minimum. Okay. In other words, f prime at c, so c being that point, equals 0. Okay. Or it's an endpoint. So there's two situations here. A max or min will either occur at a turnaround point or an endpoint. So, for example, we have 3 examples here. Okay, we have endpoint, maximum, minimum, endpoint. That's the max, that's the min. The endpoints are in the middle of this vertical interval here. Okay, now example 2. We have an endpoint, which is actually the minimum because the rest of the graph doesn't exceed this going down. Okay, then we go to a maximum. This is like, this one here would be a local minimum, but it's not an absolute minimum. Okay, absolute minimum is on the entire section of that graph. And then we have midpoint, or sorry, endpoint. And this endpoint, again, it lies between the max and min. So that's not one of like the absolute maximum or minimum. That's not the absolute maximum or minimum. Okay, and then the third example, we have an endpoint which ends up being the minimum. Okay, this turnaround point here, and if you see like these red horizontal lines, those are obviously representing the slope of the tangent. Okay, but if you see the minimum here, this is only a local minimum. Again, not a absolute minimum. Okay, and then we have a maximum, a local maximum, but then we have the absolute maximum. So when you're asked for a max and min, you are asked for absolute max and min. Okay, so algorithm for finding max and min extreme values. Algorithm is just like the steps. So here we go. If a function f at x has a derivative at every point in an interval, from like a to b, whatever that interval is, and we're actually going to touch a and like include a, and we're actually going to include b. What we do is we calculate f at x at, there's 2 different scenarios here. All points on the interval where it's like a turnaround point, f prime at x equals 0. Then what we're going to do is we're going to calculate the endpoints, a and b, f at x, right? So f at a, f at b. And then we're going to compare the numbers that we get. We're going to compare the y values. So hold on, I'm going to write that down. Compare y values. So the maximum value of f at x on that interval is going to be the largest of these values. And the minimum value of f at x on that interval is going to be the smallest of those values. So example 1, find the extreme values of the function f at x equals negative 2x cubed plus 9x squared plus 4 on this interval here, negative 1 to 5. Okay, so I'm going to go ahead and rewrite this equation, negative 2x cubed plus 9x squared plus 4, and I'm going to find the derivative. So bring the 3 down. 3 times negative 2, we get negative 6x squared plus, bring the 2 down, 18x, 4 goes away. Okay, so we are going to solve for when this derivative equals 0. These are the points that we want to consider. Okay, so let's go ahead and factor out a negative 6x out of both of these terms. So we get negative 6x bracket x minus 3. So at 2 different occasions, this function is going to have like turnaround points, and that they occur at x equals 0 and x equals 3. Okay, so let's first list all of the possible extreme values. So the possible extreme values are going to occur at max when f prime at x equals 0, so 0 and 3, and then also endpoints, negative 1 and 5. So I'm going to put these in order. We are going to test f at negative 1, then we're going to sub in f at 0, f at 3, and f at 5. And I want to point this out. None of the values 0 and 3 are outside of the given domain. So these are valid. So what we want to do is we want to find on the original graph, which is f at x, not the derivative, but on the original graph, what is happening at negative 1, 0, 3, and 5. Okay, so negative 1, we are going to do negative 2, negative 1 cubed plus 9, negative 1 squared plus 4. Okay, and we're going to get an answer. Then we're going to sub in negative 2, 0 squared plus 9, 0. Oh, it's cubed squared plus 4, and we're going to get an answer. Then we're going to sub in negative 2, 3 cubed plus 9, 3 squared plus 4. Get our answer. Negative 2, 5 cubed plus 9, 3 squared plus 4. And we're going to get an answer. So when we plug in f at negative 1, and we get 15. It's in dark. If we plug in f at 0, we get 4. We plug in f at 3, we get 31. And we plug in f at 5, we get negative 21. So what we're going to do is we are going to take a look at these numbers here. 15, 4, 31, negative 21. These are all of our y values of possible max and mins. So what is the biggest number? Well, it's 31. This is going to be our maximum. What is our smallest number? Negative 21. This is going to be our minimum. Okay, and if you think about what this actually looks like, if we're going from negative 1 to 5, we're also going to plot 0 and plot 3. Okay, the endpoint for negative 1 is at 15. The 0 is going to, we're going to have 4, and that's going to be a turnaround point. Then we're going to have 3, 31, which is going to be way up here. Okay, and that's going to be a turnaround point as well. Then f at 5 is going to be negative 21 way down here. And that's what our graph is going to look like. Okay, we have 2 turnaround points here and here, 2 endpoints, but ultimately this here is going to be our absolute max. This here is going to be our absolute min. Therefore, we have a max of 31 that occurs at f at 3 and a min of negative 21. So example 2, the amount of current in amperes is in an electrical system is given by the function c at t. I'm just going to rewrite this as I read it. Negative t cubed plus t squared plus 21t. Where t is the time in seconds, and this is on the interval 0 to 5. Okay, as a little bit of a recap, instead of using the inequality symbols, you can use the square brackets to include the number, round brackets to not include the number. Okay, but we obviously have an underline here with the inequality symbols, so we're going to include these with the square brackets. Okay, determine the times at which the current is at its maximum and minimum, and determine the amount of current in the system at these times. So what we want to do is we want to find the derivative c prime at t. We get negative 3t squared plus 2t plus 21. And then what we're going to do is we're going to set that equal to 0 and solve. Okay, so I'm taking a look at this. Let's try to solve this by decomposition. If not, you can always solve by quadratic formula. So we cannot common factor. So what two numbers multiply to negative 63 and add to 2? Well, I'm going to get the numbers. Let's go. What are the factors of 63? 1 and 63. 3 and 21, 7 and 9. 7 and 9 are going to do it. So what we're going to do is we're going to break down this middle term into 9 and negative 7 because they have to add to 2. So you negative 3t squared plus a 9t minus 7t plus 21. Now we're going to common factor 3 times. Common factor the first bracket, I'm going to common factor out a negative 3t. And I'm going to get t minus 3. Now I'm going to common factor out a negative 7 out of the second bracket. And I'm going to get t minus 3. And now I'm going to common factor out of the first and the second bracket the binomial t minus 3. So I get t minus 3 being the common factor, and then negative 3t minus 7 being what's left over. Okay, so all we've done so far is found the derivative, and let's find when that derivative equals 0. Well, we get equals, by mistake, 3 for this bracket. And if we have to solve for this, it's no problem. Negative 3t minus 7 equals 0. Let's bring over the 7. We get negative 3t equals positive 7. So our other place where we have a turnaround point or a potential max or min is going to be t equals negative 7 over 3. Okay, so coming back up here, the numbers that we are going to test are going to be the endpoints, 0 and 5. And then let's take a look at 3 and negative 7 over 3, okay? And then when f at x equals 0. I should put when c at t equals 0 for this question. C prime at p equals 0, and that occurs at 0 and negative 7 over 3. So if we think about negative 7 over 3, this is a negative number. This one is inadmissible already. Okay, because not in domain. Okay, we can also see that one of the endpoints, if we actually extended it into the negative side, one of those endpoints would be an actual turnaround point. So we're only actually testing 2 points. Oh, I keep saying 0. I apologize. This is 3. We're going to test 3 points, okay? We're going to test C at 0, the original C at 0, C at 3, and then C at 5. And I always tend to put these in order, okay? So what do we get when we plug in C at 0? And this is to the original. We want to know what's going on the original graph, okay? So I'm not going to plug these in and like write out the equation again. I'm just going to list them. So C at 0, we get 0. C at 3, we get 45. And C at 5, we get 5. So let's compare. Out of these numbers, which number is the biggest? 45 is the biggest, so this is going to be our maximum. Which number is the smallest? 0 is the smallest, that's going to be our minimum. So we can say we have a max current at 3 seconds of 45A amps and minimum current at 0 seconds, I'm going to put S, of 0 amps. So if we graph this on Desmos and remember you have to put an X, not a T, so we're going to graph negative x cubed plus x squared plus 21x. This is what we're going to get, okay? So we see possible max and mins here, right, at negative 2.3. That's our negative 7/3 that was inadmissible because it's not in the domain, okay? And we see another possible maximum at 3,45. So here's what happens. As soon as we restrict this domain on 0 to 5, okay, this is what we're left with. So now we can focus on first our endpoint, 0, 0, right? And then our turnaround point, 3,45, right? 3,45, no matter what, is going to be a local maximum, but we don't know if it's going to be an absolute maximum until we do the actual calculations. And then our other endpoint, 5,5. Okay, and we can see from this graph, if you notice the 0, 0 and the 345, like these 2 points, when I clicked on them, the point showed on the screen and it stuck. That's because Desmos is aware that these two are important values because one's like the absolute max, one's the absolute min, whereas when I clicked on 5,5, I can see this point, but it doesn't stick because it's not like a critical point that we're looking for. It's not like an important point that we're looking for. Okay, so highest value here, 45, lowest value here is 0. Example 3, the amount of light intensity on a point is given by this function, I at t equals t squared, and I'm going to rewrite this. We'll start to rewrite it. Okay, we have for the numerator t squared plus 2t plus 16 over the denominator t plus 2. So I'm actually going to write this denominator as t plus 2 in the numerator. So when we bring this binomial up to the numerator, we have to change the exponent to a negative. Okay, where t is the time in seconds on the interval, so we're restricted to the domain 0 to 14. Determine the time of minimal intensity. So we're looking for a minimum. We don't even care about the maximum. This question specifically asks for the minimum. So let's go ahead and solve for the derivative of I. So I'm going to use, just like on the side of my paper, I always do like the derivative of uv is u prime v plus uv prime. Okay, this is our u, this is our v. So derivative of the first term is going to be 2t plus 2 times the second term as it is, okay, t plus 2 to the negative 1, plus the first term as it is, which is u. We got t squared plus 2t plus 16 times the derivative of the second term. So this is chain rule. We bring the -1 to the front, we write the bracket as it is, and we subtract 1 from the exponent. Now the chain rule is because since inside of this bracket is no longer a t, it's t plus 2, it's a full function, we have to multiply by the derivative. But that's easy because the derivative of t plus 2 is just 1. So what I'm going to do is I'm going to rewrite this. So I'll rewrite the first term, first term, and I'm just going to collect a little bit of the second. Okay, so -1 and 1 just go to negative, and then we can just write t squared plus 2t plus 16, bracket t plus 2 to the -2. Okay, so most of this is math. Okay, at this point, what we're going to do, so if we set this equal to 0, it's really difficult because this is not fully factored. We can't just branch off and solve. So what we're going to do is we are going to see if we can factor anything out of these two terms, and we can factor out a t plus 2. Okay, and again, we're going to factor out the lower exponent. So that's -2. So what we get is our common factor, which is t plus 2 to the -2, and then what's left. So in the first term, we have a 2t plus 2 left, and then these exponents, remember, this is -1 minus -2, which is 1. So we're left with t plus 2 minus, those go away, so t squared plus 2t plus 16. Okay, and now what we have to do is I'm going to go ahead and FOIL these two brackets. I'm also then going to distribute this negative sign into the second bracket. So this is just a lot of math here. We get 2t squared plus 4t plus 2t plus 4 minus t squared minus 2t minus 16. Okay, so let's go ahead and collect like terms. So we're still dealing with the derivative of I. So we have t plus 2 to the -2. Now we have t squared, right? 2t squared minus t squared. Then we have 4, 5, 6. Oh, these cancel. So we have plus 4t. And we have 4 minus 16, which is -12. Okay? Is this factorable? So what two numbers multiply to -12 add to 4? Can we factor this? 1 and 12, 2 and 6. 2 and 6 work. We would have to have the negative on the 2. So our fully factored form of this equation is t plus 2 to the -2, t minus 2, t plus 6. Okay, so we get the answers t equals 2, t equals -6, and then taking a look at this one here, I'm going to actually compute this. So if we have t plus 2 to the -2, and we have to equate that to 0, we can raise both sides to the -1/2, which is essentially just going to get rid of the exponents. And now we have t plus 2 equals 0, so t equals -2. Okay, if you remember, this is on the domain 1 to 14. So these ones cannot be solutions, okay, not in domain. Okay, this one is not in domain. So now what we want to do is we want to test I at, oh, I should have put a 0 here, form-wise, because this is the point where we actually equated it to 0. My mistake. So we're going to test I at 0, which is our endpoint, I at 2, which is our, and so we're going to test I at 2 and I at 14. Okay, 0 and 14 are the endpoints. 2 is the only possible turnaround point within those endpoints. And we get 8, 6, and 15. So the question only asks, determine the minimal intensity. So we have to just find the minimum value here, which I get a 6. So therefore, the minimum intensity is 6. Which occurs at 2 seconds. I was just looking for the units. So if we were to graph this, we have t squared, so x squared plus 2x plus 16 all over t plus 2, so x plus 2, okay? So this is what this graph looks like, but we are going to restrict this to the domain. So squiggly brackets, 0 includes x includes 14. So we can go ahead. Let's get rid of those. Actually, let's put those back in. Okay, so we get 0, 8. Okay, see how again that's, oh, the endpoint 0, 8, it is picking it up this time. Okay, 2, 6, and then 14, 15. So the minimum is definitely 2, 6.